So stuff is going on here. We're just kind of ducking and covering today because there's nothing else we can do. There were a couple of reading assignments over winter break there in the campus. If you hadn't seen those, here they are. 96 to 97 is in chapter 4, and then 184 to 189 is in chapter 8. I really like how the book presents this stuff. I just wish it was kind of all together because they just kind of throw this center-directed acceleration thing at you, and then you don't really understand why it's there until you get to this course. So we're just going to combine those things together, be a little bit disjointed. And then the mastering that was due tonight and then was due Sunday is now going to be due Tuesday, I think. Okay, just because I want to have some time in class to go over those types of problems we have not yet. We'll talk about it hopefully a little bit towards the end of the hour. What I'm going to ask you to do here in a second is put together a whiteboard for your lab stuff. And this lab is already really tricky to unpack if we're here. And so then to not have a day in person to pre-lab it, we had to do that via Pear Deck. B, only have 35 minutes on the day that we actually collect the data. And then C, not see each other again until the end of the week. Yeah, it's kind of all over the place, but hopefully we can kind of tie it all together and put a bow on it today. I want to make reference to a couple of understandings here that kind of come out in the analysis, okay? So you've got this stopper on a string spinning around in a circle. If I spin it slowly, you can kind of see how it's carving out a cone around the top of my head. Okay, it's not in a flat circle per se with the string. Even if I spin it fast, it's still at a slight angle. And that's because there's a downward force of gravity on the stopper, and that tension has to be at a somewhat upward angle then. The problem was when we were pair decking this, a lot of us kind of have a default default arrow length. Kind of draw all the arrows the same. So this is a really common free body diagram for the stopper on pair deck. But in fact, the tension is something like 10 times the magnitude of the gravitational force. Okay, if I have a 1 Newton tension, it's 10 times the gravitational force in the stopper. So it doesn't have to really be pointing straight up to balance that out, but it does have to be inclined slightly. And that's what I'm showing in this diagram here. If I make a force addition diagram with the tension felt by the stopper and the gravitational force felt by the stopper, you can see they're very different in size. So my chain of reasoning again, the hanging mass is not accelerating up or down. It's just kind of hanging there underneath the tube. That tells me that whatever this gravitational force on the hanging mass is, the tension force matches it. Those forces balance. If I know the tension on the hanging mass, then I know the tension on the stopper because they're connected to the same string. So this tension has to equal this tension has to equal this gravitational force. And then by Clinton geometry, I'm going to make an argument that the hypotenuse and the side of the triangle, if it's a really long, skinny triangle, well, those are basically the same. So if this tension is 1 Newton, that's 1 meter to scale, the FU that I get is pretty much 1 Newton as well. Because this is at a slight upward angle, that unbalanced force is pointing towards the center of rotation. So that's why it's called a Fuch. So Fuch equals Ft stopper equals Ft hanging mass equals Fg hanging mass. That's what allowed us then to create a graph of unbalanced central force versus angular velocity or unbalanced central force versus tangential velocity. Okay? That's what I'm interested in hearing from you about. So if you could, grab a whiteboard for your group and put together your stuff. Make sure you're labeling your graph axes and all that. Make sure you put number value and units on the things you didn't change. But let's go ahead and get after that. What's up? All right. We've got 5 boards up here. Hopefully that's enough to get some things out of this thing. What I want you to do is kind of take a 30,000 foot view of these boards and look for any kind of like similarities and any kind of differences. Okay, what are some things that are always the same? What are some things that are sometimes the same? Rhoda, give me an always thing here.
The graphs are curved.
They're all curved. They're all curved up. Yeah, they're all top opening parabolas. Okay. What else do we got here? Bradcock, what do you got?
Java for vertical intercept is 0.
Oh, the vertical intercept is 0. Makes sense of that. Should the vertical intercept be 0? Why? Run that by your neighbor really quick.
I know how to do that, but I don't.
So if no Fuchs are given, right? If the Fuchs is 0, what should be happening here? You're going in a circle? Nah. Okay, so you don't have a circular velocity. All right. Terwilliger, something else you're noticing?
Well, all of the constants seem to be relatively similar.
All the constants seem to be relatively smaller. 0.022, 0.019.
It's supposed to be 0.01.
0.01. You're just saying that because all the other ones are small. 0.018 and 0.01. Okay, so they're kind of smallish numbers. Okay. Anything else you're noticing that's similar or same? William, what do you got? Or you can throw out something that's different, I guess, if you can't find anything the same.
Some people have like kilogram meters for their constant unit.
Okay. So here I see kilogram meters.
And that's kilogram divided by meters.
That's kilogram over meters. So who's got it right? Who's got it wrong here? Run that by your neighbor really quick. What's up with the different units?
It's a kilogram over meters. Cancellation works. Newton doesn't.
Should it be kilogram times meters or kilograms per meter? Ronan.
Per meter.
Per meter. So why'd they screw it up?
Unit cancellation somewhere.
What's that?
Unit cancellation.
Unit cancellation. Ewoks, did you cancel your units incorrectly?
Probably.
Dude, I'm the one that did the units. I didn't cancel them wrong. You canceled them wrong. Yeah.
Why though?
So let me walk you through the unit cancellation here. Okay, important understandings. Radian per second is really per second. It's 1 over seconds. Radian's a placeholder, not a unit. Okay. The equation here that Alex had is y equals ax squared. Y is newtons. It's kilogram meters per second squared. X was omega. So x squared is omega squared. This is 1 over second squared. And so I said, hey, Alex, what do we multiply by 1 over second squared to get kilogram meters per second squared? And Alex said kilogram meters. And I said, yeah.
I had thought since it was velocity. Oh wait, are you doing? Is it the tangential velocity?
Oh,
that's why.
Did we find a difference? What's the difference?
It would be tan versus.
Yeah. Alex has omega. Did anybody else have omega? What are you? Tuscan Raiders. Okay. And I didn't get a chance to give them my feedback on what a radian is. Okay, and that would have helped. And then also that they're squaring that whole angular velocity thing. So yeah, long story short, kilogram meters. So this is kilogram meters. This is kilogram per meters. Jawas. So with that, so they have the same units, they're just doing a different function. Some are multiplying, some are dividing. Okay? Important nature of science thing that I'd like us to understand when we're doing labs like this is that constants in your equation, which by the way, do we all have the same constant? Kind of, they're in the ballpark, right? Constants in your equation often relate to things that were a constant in your data collection. Okay? And so I already chatted with the Wookiees about that, or the Wookiees figured it out on their own perhaps. The constant values were in kilograms and meters were the stopper mass and the string radius. So theirs is kilograms per meter. So they take their 0.01 kilogram and divide it by their 0.66 meter radius, and they get 0.02 kilograms per meter, which is basically what they had for their thing there. Droids did the same thing, right? Took their stopper mass divided by their radius and got 0.019 kilograms per meter, which is pretty close to 0.018 kilograms per meter. So long story short, Fook equals mass of the thing going around in the circle, that was the stopper, right? Divided by radius times v tan squared. Now I wouldn't write it that way. I would write it like this, because then you're going to notice, hey, that looks awfully similar to what? What do you think, Walkie? What does this remind you of? FU, yeah. Hey, what do you know? It's a different kind of acceleration, though. This is the centripetal acceleration. So I can write this as Fook equals Mach, and AC is V tan squared over R. We're changing our definition of acceleration. Previously, acceleration was the slope of the velocity versus time graph, or the time rate of change of the velocity. It still kind of is that. But if we're talking about going in a circle, V tan squared over R is what tells you the acceleration value. That's the acceleration that led to this coordinate pointing towards the middle. Okay? And then real quickly over here, they're taking kilograms times meters. So over here, it's Fook equals mass times radius times angular velocity squared. So Fook equals m r omega squared. And so another way of calculating the centripetal acceleration is taking the radius times the angular velocity squared. Both ways of doing that give that acceleration a unit of meters per second squared, provided that your radius is in meters and all that other good stuff. So those are the important fallouts from the lab. Make sure you got those equations jotted down somewhere. We're going to need them for the old thing. All right. Ronan, you can dip if you want. Just know there's the mastering assignment that's due on Tuesday, and these readings from the book that might help make sense of some of this stuff. I don't know. Okay. Oh, and then there was this other thing I was going to do. If you got to go somewhere for AFT, you can. If not, you can stick around and watch this thing. I had a lot of free time. I didn't have a lot of free time. I had 3 small children at home, so I was constantly having to run around and give milk to somebody over here. Oh, now you got something going on over here. I gotta go deal with this. And then back over this way, and then that happens. And now what do? How do you get that down from there? Okay, very carefully. Oops. Or then sometimes it ends up doing this. Or if your arm gets tired, oh, it does that, right? Okay. So we'll talk a little bit more about the free body diagrams for this thing tomorrow. Not tomorrow, Monday. We're not going to see each other consecutive days ever again, are we? All right. Go ahead and take a picture report if you want. Make sure I get a Desmos of everything. Make sure you give me the explanation of your constant. And yeah, that's about the size of it.